Ladies and gentlemen, welcome, boys and girls. Today we are taking a look at the binomial theorem from the perspective of sigma notation. We're eventually going to tie it to that and figuring it out as a series and finding the sum of a bunch of terms. Now, we've done binomial experiments in the past in previous courses, probability, different things like that, but we're actually looking at the actual straight-up binomial theorem today. And what I want to point out, let's see, the binomial theorem is all about expanding binomials raised to a power. So x plus y to the 0th power, that would be the same as 1x to the 0, y to the 0. Actually, it'd be really cool if I switched colors here. I might. I'm going to rewind and switch colors here. This is going to be a lot of colorful work here. All right, so let's see. I'm going to have x plus, man, this is going to be, I don't know, guys, what do you think? It's going to be so much switching back and forth with colors.
I like colors.
Yeah, it's too much. It's too much. So let's see. So this is the same as 1x to the 0, y to the 0. What's this whole term equal to? 1. And I think you guys would agree with that, right? So x plus y all to the first is the same as 1x to the first, y to the 0, plus 1x to the 0, y to the first, which I want to point out is the same as just x plus y. Right?
Hang on, why are we putting in 1x to the first, y to the 0?
It's going to help us recognize a pattern in a moment, is all.
Oh, yeah.
X plus y all squared will be 1x squared, y to the 0, plus 2x to the first, y to the first, plus 1x to the 0, y to the second.
Hey, do I see a Pascal triangle coming on?
Our old pal Pascal. Let's see. X plus y to the third would be
1x cubed y to 0 plus 3x
squared.
cubed x squared y to 3 plus 3x to the first y squared plus x to the 0.
Hang on, 3x to the first,
Okay.
y.
Oh, yep. So that would actually be 1x to the fourth y to the 0 plus 4x cubed y first.
Let's see. 1x to the fourth, y to the 0, plus 4.
Hang on.
Yeah, I'll leave it written down there in a moment.
Plus 6x squared y squared plus 4x to the first y cubed.
Yeah.
1x to the 0 y.
Hang on.
Don't worry, sir. I'll have it up in a moment.
3 plus 3 is 6.
See 3 plus 3, can make a diamond shape. Or a little arrow pointing down. 3 plus 3 is 6.
So let's see. So, what patterns do we realize?
Pascal's.
Okay, so the coefficients of the terms 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. What would the coefficients?
10, 5, 1.
1, 5, 10, 10, 5, 1 would be the next set of coefficients.
Are going like
6, 15.
Have we done something with this before?
Yeah. So 5 is the sum of the 1 and the 4. 10 is the sum of the 4 and the 6. 6 was the sum of the 3 and the 3. Right? So the coefficients are the sums of the two terms above it. Okay?
1, 6, 15.
What other patterns do you see?
Fibonacci sequence.
Well, more obvious ones.
Wait, so what was that last one again? 1, 6.
What, for which one?
White said the next line would be 1, 6. 1, 6.
1, 6.
20, 15. Sorry, could you slow down?
Well, we're not going to go any further. But it would just be the sum of
Yeah, it's
the
on that little orange sheet.
previous two.
Okay.
So that's where the coefficients come from. Now, we also had the coefficients come from somewhere else before, friends in the back. Do you guys remember how we could have found those coefficients another way without having to have generated this entire Pascal's triangle? Like if I wanted to find out what the coefficient of like in the 20th row was, I wouldn't have to draw the first 19 rows of Pascal figured out.
Well, always starts with 1.
Starts and ends with 1.
It starts and ends with 1. We know that much. Does anyone remember?
The second number is the number of the row.
The second number is, so this 4 is the same as the degree, right? This 3 is the same as the degree. Yep, so that works.
And then the x's and y's are only like it's showing
Guys in the
4,
back, come on.
And like if you do that weird thing that fools all the children, where you're like, oh, and then oh, where that's what that thing is doing. All the coefficients.
For the, are you talking about not the coefficients, but
the exponents.
the exponents? Okay, so let me see if I can do this. This little hand magic trick. Here we go. So what a student just demonstrated, suppose the exponent was 3. All right, so it would be x to the third, y to the 0. All right, y is my right hand here. And then she went like this and like shifted it over, right? So it'd be x squared, y to the first, and then like that, right? And x to the first, y squared. I really like that analogy. That's perfect. And then x to the 0, y to the third, right?
That one actually looks magic.
Yeah. So I think that's a perfect. Oh wow, it's got my last name right there.
That camera is really good for that. It makes it look like
Because it's like the frame delay. Yeah, that's excellent. So another way to describe the pattern with what these coefficients are doing. Look at the x's. For my first term, it's 3, 2, 1, 0. And where'd the 3 come from? The 3 came directly from that. So for the x's, it's descending from highest degree to lowest degree. And for the y's, it's 0, 1, 2, 3. Right? So it's ascending for the
I'm
y's.
guessing it will always be a 1 on the outside. So, keep it up to discover.
And it will always be a 1 on the outside. This would always be the degree of the binomial, right? And things like that. So you guys don't remember the...
I don't remember anything.
Well, here, check this out. This is the book's description of patterns in the binomial expansion. Let's see how many of these patterns we hit. So do not write these down. Do not write these down. But let's just at least discuss these patterns. So it says the following patterns can be observed in the expansion of x plus y all to the n. And let's see. So it says the expansion has n plus 1 terms.
Yeah. That's
Okay. So when n was 0, there was 1 term. When n was 1, there was 2 terms. When n was 2, there was 3 terms. Okay. So I didn't spot that pattern. The first term is x to the n. Gentlemen, quiet please. And the last term is y to the n. Okay? So that makes sense, right? 1x to the fourth, 1y to the fourth, right? So that's a good pattern. In successive terms, the exponent of x decreases by 1, and the exponent of y increases by 1. So there's a little trick the kid with the finger flip from one hand to the one other hand, right? You know what I'm talking about. So that we noticed. Problem 4, it says the degree of each term, the sum of the exponents of the variables is n, right? So this term, the sum of the exponents, the degree of this term is 4. The degree of this term, I clicked. Don't click. There we go. The degree of this term is 4. The degree of this term is 4. right? So the sums of those exponents is always going to be whatever degree it was raised to. All right. Let's look at this other one. In any term, if the coefficient is multiplied by the exponent of x and the product is divided... Whoa, what? Oh, you know what they're describing here? This is the part that we were talking about that you guys didn't realize. Well, before I do 5, let's look at 6. The coefficients are symmetric. That is, the first term and the last term have the same coefficient. The second term and the second from the last term have the same coefficient, and so on. Right? So you guys notice that 5 and 5, 10 and 10. Right? There's symmetry. Actually, you could kind of say it's palindromatic, almost. I mean, if you consider... unless you wanted to really make this be 0, 1 instead of 10, but really...
5, 10, 10, 5,
Come on.
5, 10, 10.
But right, it's somewhat like a palindrome. And then in problem case 5 here, let's consider what case 5 is saying here. Because this is the pattern of those coefficients that we were looking for. It says in any term, if the coefficient is multiplied by the exponent of x. All right, the coefficient is multiplied by the exponent of x, and the product is divided by the number of that term. The result is the coefficient of the following term. Okay, so let's pick an example. All right, 4x cubed y to the first. All right. I've never noticed this. This wasn't exactly the pattern that I thought I saw, but this is interesting. It says, so if I multiply the coefficient 4 times 3, all right.
Oh, I see. Yep.
Hang on, should I be writing this down?
Yeah, sure. Not any of the text here, but just this little example. And divide by the number of that term. What number term was this one?
The second term.
The second term.
Then it would be the 6. Yeah.
Wow, that's pretty cool. All right, so let's summarize this. So this was coefficient. This was degree of x. And this was number of term. And then this ended up equaling the coefficient of next term.
So that's how you get the row Pascal.
Yeah, I never knew this particular pattern. I was going to relate it to something else. The other explanation for 5 is if... let's let the following be true. Let's see. I'll just say coefficients. Let n equal the degree.
Wait, what do you mean coefficient of the next term?
So 6. So
Coefficient up to 1, yeah.
so this one would then be plus 6x squared y squared would be the next term. This 6
okay.
is the next term's coefficient, right? And that is what we had up here, right? 6 was the next one. And then that's saying 6 times 2 is 12, divided by 3 is 4. And then I get the 4 over there. That's a pretty cool pattern. I never knew that one. I like it. The one that I think of, let's see, R is... let's see, how do I describe this? I think R would be the degree of x. Although it technically would also work for the degree of y, which is weird. But it turns out the coefficient for any term will be combo n comma r. This is how we did it back in our probabilities days.
Hang on, what do you mean n degree?
The degree of the entire polynomial. So in this case it was 4. It was x plus y to the 4th, so n would be 4. I'll do an example of it.
I don't even remember.
So x plus y to the 4th,
All to the 4th.
all to the 4th, yep. So I'd say n is 4. And let's say I'm looking for the third term. All right, the third term's coefficient. So which term am I talking about? I'm talking about this term. So I'm looking for this. What is the degree of x in this term? 2, okay? So the third term means r equals 2 in this case. So what is combo 4, comma 2? Does anyone remember that formula?
4 factorial. 4 factorial, 2 factorial, 2 factorial.
Oh, God. I like the other one.
Oh. Wait, does C always fit the coefficient?
No.
No.
Combination.
Combination from probability. Good question. So let's see. So this is 4 times 3 times 2 times 1 over 2 factorial, so 2 times 1 times 2 times 1.
And look.
And now if I cancel out, ching, ching, and then 2 goes into 4 twice, I get 2 times 3 is 6 over 1.
I really like the other one better.
Yes, I do as well. That is kind of neat, because the other one is somewhat iterative, where it will generate the next term in the series, which is always what you're looking for when you're writing it out.
So that's the coefficient of the next term?
That's the coefficient of the actual term. So this would be the coefficient of the third term.
No, it starts to get harder as you got into bigger numbers.
Yeah. Yep. Absolutely. But we'll end up using this fact, which is one that we did back in the days of binomial experiments. So this would have been, for instance, me flipping the coin 4 times and wanting exactly 2 tails. And there are 6 ways that that could occur. And then I would have multiplied by x to the second, where x was the probability of success, multiplied by y to the second, which y was the probability of failure. And that's what that ended up representing back in the probability days. So all sorts of interesting stuff recognized in this pattern, right? And for Pascal's triangle, I gave you a list on our formula sheet. I thought I had some over here. La la la, but I do not.
Okay, they're telling me.
Oh well. But Pascal's triangle looks like this. How far down do I go on our little formula sheet? Actually, I'm just going to swipe this real quick. Kablam. Here's mine. Yeah, so I go down to the
11.
x to the 10th or the 11th row, technically. And within Pascal's triangle, there's actually all sorts of crazy patterns. If you're interested, I actually have a college professor's book, and he has quite a few patterns in here. But yeah, there's all sorts of weird stuff about diagonals, and there's like the stocking method, where if you make like an L-ish shape, there's some weird fact about the sum, and all sorts of crazy patterns in here. But yeah, the idea behind Pascal's triangle is that any term is the sum of the 2 terms above it. All right, and we can use this to, generate our coefficients as well. Okay, so having Pascal's triangle can be nice. But
Sounds like a modified Fibonacci sequence.
Yeah, it's a similar iteration is the idea behind it, that any term is the sum of 2 previous ones.
And the Fibonacci sequence is in Pascal's triangle.
So let's do an example. So let's do, I think I want to just skip right to a fancy one. Well, no, we'll do an easy one first. Let's do expand x plus y to the 6th. All right. So my first term, actually sometimes what I like to do is specifically go through and write all the coefficients first. So this will be 1, 6, and it's easy to do the coefficients first if you have Pascal's triangle with you, which I stole yours, didn't I? So this would be 1, 6, 15, 20, I might run out of room, and then 15, and then 6, and then 1. All right? So there's multiple ways you could do this. And then I like to go through and write all of the x's. So this would be x to the 6th, x to the 5th, x to the 4th, x to the 3rd, x to the 2nd, x.
Two-dimensional.
Right. X to the 0.
Yeah, I don't have any room in mind for
Yeah, it
the
is
y's.
tricky fitting it. Yep. And then we'll go through and add the y's. So this would be y to the 0, y to the 1st, y to the 2nd, y to the 3rd, y to the 4th, y to the 5th, y to the 6th. That's my classic 5 looking like a pirate's hook
Oh my
coming
God,
out
look
of
how
a
close
sleeve.
mine are together.
Yeah, that's all right. We'll get the idea. And then the signs. Now, if this is x minus y all to the 6th,
Oh, Lord.
the signs will actually be alternating. All right, and the first term would always be positive. So since this is plus, these will all be pluses in between. But if it was minus, it would have been plus, minus, plus, minus, plus, minus, and go all the way down. So plus, 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 plus.
I don't have room for
Plus.
pluses.
That's okay, as long as you get the idea. All right, so you can use this to expand these things without a terrible amount of difficulty. All right, so let's do one that's a little bit more interesting. What if I've got 2x minus 3 all to the 4th? So let's figure out my coefficients. Or actually, maybe this one, instead of using Pascal's triangle, maybe we'll do the multiply the coefficient by the degree and divide by the term to figure out the next coefficient trick. Let's see if we can do that. I'm not well trained on that one. My first term is going to be 1 times 2x to the what power? 4th times, technically, negative 3 to the 0, right? So my next coefficient should be 1 times 4 divided by 1, because this is the first term, right? So I'm going to have a 4. All right? Times 2x to the 3rd times, and I'm going to use positive 3's here and just use my alternating signs trick. So this would be 3 to the 1st, right? So if I want to figure out my next coefficient, I do 4 times 3 is 12 divided by 2, because this is my second term. So that's 6 times 2x squared times 3 to the 2nd. And then I'll do 6 times 2 is 12 divided by 3 is 4 times 2x. The x exponents are decreasing. The y exponents are increasing, right? And then 4 times
Wait,
1
you
is...
forgot to put in 3y. You just wrote 3.
Well, yeah, I decided to just have it be 3.
Oh,
In this
right,
one.
yeah.
So y is the 3. And then the last one, 4 times 1 is 4 divided by, this is the 4th term, so divided by 4 is 1. And I get a coefficient of 1, and 2x doesn't show up, but 3 to the 4th does. And as I said, because this is negative, well, imagine for a moment, what if these 3's were negative? Right, negative, first of all, this would be positive. Negative 3 to the 1st, odd degree, would have a negative outcome, right? Negative 3 to the 2nd, even degree, would be positive. Negative 3 to the 3rd, odd degree, would be negative. And so you can see where the alternating signs come from. I'm fine if you add them in at the end. Okay?
How do we know if the first one's minus or plus?
The first term is always positive. But you wouldn't put a plus sign in front of the first term, right? Because that'd be weird.
But
How do you get
unless you
more
were
than
to
zero?
decide, which is the subtraction side.
Let's see, what was that question in the back?
4 times 3, and then you divide it by 2 since it's the second term.
Right.
You get 6.
So 4 times 3 divided by 2, where 4 was the coefficient, 3 was the degree of the x,
Wait, should
and
I
2
write
was the
this
number
down?
of the term. Nope. And that's how I got 6. So that is, I do like that trick. That is pretty good, without having to use Pascal's triangle.
So you always use 4 times 3 divided by 2?
No, it's the coefficient times the exponent of the x. That's what we wrote up here, man. Come on, man.
I'm looking at that.
Right, right.
And oddly enough, it's the same row.
Yeah, I happen to do that again, yeah. Yeah, there's a lot of different patterns to take in here.
The third one would be 6
So let's
times
simplify
2
this.
divided by 3.
2 to the 4th is
'Cause it's
16.
the coefficient is
x to the 4th
6.
minus 2 to the 3rd is 8.
And then it's the third term.
8 times 3 is 24. 24 times 4,
96.
96.
Times
Yep,
the
x
coefficient
cubed.
of the x, which is 3, or the exponent of the
Let's
x,
keep simplifying. 2 squared is 4. 3 squared is 9. 4 times 9,
36.
36 times 6,
216.
216 apparently.
In the equation about the x term
X squared.
is not good.
And now let's keep multiplying. 2 to the first times 3 cubed, 27. So 2 times 27 is 54. Times 4.
216. Yeah, 216.
Yeah, sometimes you do end up having them equal the same. It's possible. If they have the same, prime factorization. Times x. And then 3 to the fourth, I believe, is just plus 81. So I'm able to expand that. And what's nice is back in the days of Algebra 2, I had you memorize patterns for a plus b all squared and a plus b all cubed. But now you can just figure out a plus b to the 10th. And you could figure it out on your own without having to have memorize a singular pattern. You've memorized a pattern that generates patterns. It's like making a robot that makes robots.
It's weird.
Right?
Inception.
So, but what if your car was then able to make more cars? Actually, a movie from the 80s that I'd highly recommend, which I believe is actually a Spielberg film, it's called Batteries Not Included. It's about these cute little alien robots. It's wonderful. And then a little baby robot. I won't talk about it. It's sad. It's sad. But they're reproducing robots. That's how you have baby robots. I actually heard a question on the podcast.
But without guns.
Sure. I heard a question on the podcast, and I found this very intriguing. In the Pac-Man universe, all right, this might just take 30 seconds for those of you watching online. You can fast forward. In the Pac-Man universe, are the ghosts dead Pac-Men? Or were they just always ghosts? And if they were always ghosts, then are they actually ghosts? Or are they just in their own species? But then when Pac-Man...
Perhaps they're a species.
When Pac-Man kills a ghost, it's like a second-degree ghost, and it's just eyeballs that goes back to like the little hideout that it has.
It sounds like
Maybe the
No, it wasn't Day9, but...
maybe the ghosts are a protoplasm-based species.
Right, but then they wouldn't have been ghosts to begin with. The idea of a ghost is it's something that was came from the result of something dying.
The large pixelated ball that causes them to be weakened.
I don't know.
Should we eat them?
Maybe it emits an electromagnetic field that disrupts their protoplasm
it could happen.
structure.
Although, then I was thinking if the ghosts were dead Pac-Men, then the eyeballs are like a third-degree ghost. Right? So it's Pac-Man, when he dies, he becomes a ghost. When the ghost dies, it becomes eyeballs.
Fourth degree ghost, being kind of the color one would be first degree, the blue one would be second degree, the eyeballs would be third.
Well, I would say the blue one's just a weak ghost. Like, one that's like
vulnerable.
nauseous.
One that's been shot with a nuclear power.
But then the question is, when Pac-Man dies, he just goes bloop, 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 and like his mouth opens so wide that it closes in on himself. And I don't think he becomes a ghost. So I think he turns into nothing.
He turns into a black hole.
Yeah,
Turns into
he
oblivion.
folds in on himself. Like,
That would be
what?
such an awesome.
That's terrifying.
That would be so much cooler though.
That'd be the worst way to die. Is like dislocating your jaw snake style and then just like turning yourself inside out into nothing. What? Oh. Anyways, okay. Back
Mr. Waddy,
What's
that'd
that?
be such a cooler ending to Pac-Man though. Like when he dies, he just turns into a black hole and the entire like mass
Screen
sucks
just-
in,
Yeah, that's terrifying.
and then it's just like a black screen and the game
Actually-
turns off.
I don't want to do an example just yet. Let's see. We'll binomial theorem. So this is the way we've seen this before. We had x plus y to the n. Right. And this is equal to x to the n plus n times x to the n minus 1 times y. Right? So you guys agreed, we agreed that earlier that the second coefficient was always equal to the degree, right? And then plus, and now this is just the definition of a combination. Well, actually, oh wow, it's a pre-reduced combination. N times n minus 1 over 1 times 2 x to the n minus 2 y squared. Yeah, we're not going to fit this all in one line.
What's the x? Is that like a separate thing? Or is that multiplying by that factor?
It's all multiplying. The plus signs are the only things that are separating the...
Oh my
The terms.
god,
What?
this is confusing.
So basically, it's just showing us the pattern we just did to find out.
Right. This right here,
Why does it say 1 times 2? Why can't it be 2?
That's 2 factorial.
yeah, 2 factorial. I agree, it could just be 2. But they're trying to generate the pattern for us so we can spot what's going on. And then the next term,
I don't have any room.
yeah, I might actually do a plus sign down here. That's what I'm going to have to do as well. Would be n times n minus 1 times n minus 2. Yeah, this is just, it's just the combination formula partially simplified. 1 times 2 times 3 times x to the, what's the exponent?
Minus 3.
N minus 3, right, because x's are going downhill, and this would be y to the third, right? And then plus dot, 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 and this would keep going all the way until I got to
N.
y to the n.
Oh my god.
Right, so that's the formula.
They are now
Simple enough.
find out a pattern by looking at our sheets.
So let's see, what if, craziness. What if we tried to write this formula in terms of sigma notation?
What if we try not?
Because it'd be actually a quicker little formula for us.
Pretty sure it would be y to the n on top of the e.
Let's see, so here we go. Here's our formula. X plus y to the n. Let's write this in sigma notation.
Equals sigma.
It's a sum of, and this is going to be interesting, they'll use r equals 0 to n. R is going to end up being our exponent of the y's, is maybe the easiest way to think about it. So right in the first term it was y to the 0, and then y to the first, y to the second. All right, so r is going to be that part, right? So y goes from 0 to n. Or, sorry, r goes from 0 to n. And what are we going to have? We're going to have combination. So the sum of n factorial over n minus r factorial r factorial. Man, I can't write a good r right there.
I'm
R.
pretty sure the thing on the sheet doesn't have a factorial up
Did I forget it? I hope not.
there. It says 1.
No, it's before.
I'll double
Oh,
check
yeah,
it.
the
Oh, they wrote the r before.
Factorials before that, but the after factorial is 1.
Oh, that's just an unnecessary one. That should have been an exclamation mark. That's all. Terrible mistake. Sad, Mr. Waddy. And then let's see, and then we'll have times x to the
N. Minus r.
Which makes sense. Because
right. So for the first term, n minus 0,
Times
n
y.
minus 1, right?
R to the top. R is the
Right. N minus 2, and then times y to the r.
Oh, that's simple.
that makes sense.
Wow, I had no idea sigma notation could make something simpler.
Are you being sarcastic? I can't tell.
Oh, I was being sarcastic.
Well, it's shorter writing this than this huge list.
And it
Unless
actually
it was just-
kind of makes more sense to me
Unless n
than
is
just
1.
writing this list
Yeah.
endlessly.
Yeah.
Or if n was 0.
So this is the binomial theorem written in terrible. My box messed up. Written in sigma notation.
Mr. Waddy,
What's that?
are we ever going to have to find the limit of sigma notation?
Yes.
Oh my
That would
god.
be calculus.
This year?
This year. By the end of this class, we're going to take a glimpse at that. So let's do an example with this, and then we'll call it. What if I want to find No. Find the fifth term of, and that's a weird F. I'm going to fix it. That's a little better. Of 4a plus 3b all to the 7th. So, in order to do this, first of all, tell me what is the x part equal to?
X equals 4a.
Yep. Y is 3b. N is
7.
7. And R?
5.
Let's analyze this. I'd like to say 5,
4.
What is R?
but is it?
It's 4.
It's 4? How do we know?
Because the first term for the first term, r equals 0.
Exactly. So for the first term, R equals 0. So if I'm looking for the fifth term, 1, 2, 3, 4, and then the fifth term, R would have been 4. So R is 1, R is 1 less than the term we're on. I guess might be a helpful fact.
So it's 5 minus 1.
So we'll write that, yeah. R is 1 less than the term, because R starts counting at 0.
So if you ask for like the sixth term, it would be 5.
Yep. So let's just plug all this in. And now I'm not doing a sigma here. I'm going to scratch the sigma part because I'm just finding a particular term. So we're just going to plug it into this. Right? And I think you guys agree, finding the fifth term of this, you wouldn't want to use our Pascal's triangle or even the coefficient times the exponent divided by the term method. That one you might know. No, because you'd have to find the coefficient all the way from the beginning. Yeah.
Well,
It'd be a lot of work.
Put the second one in, because that one's
Yeah.
easy to find.
But I mean, finding the fifth term, it'd be a lot of work using those other ways. So it is beneficial actually knowing this particular formula. So let's do this. So I'm going to have 7 factorial over 7 minus 4 is 3 factorial, 4 factorial times x, which is 4a, all to the n minus r. 7 minus 4 is 3. And y is 3b, all to the r. So let's see if we can simplify this. Well, I'm going to do that as 7 times 6 times 5 times 4 factorial, intentionally.
And 3 factorial is 6.
And then 3 times 2 times 1 times 4 factorial. So I kind of pre-plan what I can cancel there. 4 to the third is that 64? I think. A cubed. 3 to the fourth is 81. B to the fourth.
Cross out 4 factorial.
Ching,
Cross out
ching,
6,
ching, ching, ching.
35.
So I'm going to have 35 times 64 times
Hang on,
81.
81b looks kind of like 8 pounds.
It does. That it does. Let's see. So I'm going to rely on a calculator for a moment here. So let's see. So what am I doing? I'm doing 35 times 64 times 81. Right? So I get a coefficient of 181440. A cubed b to the fourth.
Whoa, I wouldn't have done that number really easy.
181.
Of course. So that's a whole bunch of stuff on the binomial theorem, ways to expand binomials raised to pretty much any degree, as long as it's an integer, I suppose. And then we also threw in that little bit of sigma notation, which I thought was a sweet little deal. Right, good stuff. So So I think we're pretty good. So we can say bye to our internet friends. Bye, internet. Bye.